Alright, so in this tutorial we're going to look at the ideal Carnot cycle, which is a different set of processes that give us the optimal efficiency for a heat engine. This was set up 150 years ago or so by a Frenchman, Sadi Carnot. It is taking a gas through very, very slow processes that are ultimately reversible. That's an important fact, but we're not going to emphasize that. But I want to highlight the key processes or steps in this cycle, and we're going to introduce a new step that we didn't see in our previous example. And then what we're going to do is sum up all the different ways you can move on a PV diagram and relate the change in internal energy, work done, and heat flow, as well as the name. So let's do with the Carnot cycle. Okay, so we have, if you look at this, we go from 1 to 2 to 3 to 4. Notice that it's a clockwise steps, so that tells us that it's a heat engine. But notice the shapes are all curved. Okay, and we've already seen one curved type of process in isothermal, but we see a different type of curve here. That's going to be a new process. So pay attention that we see that 1 and 2 are on an isotherm of 300 Kelvin, and 3 and 4 are on a different isotherm. Okay, so let's try to go back and forth between these two. So if we start from 1 to 2, which goes from here, we're staying on the 300 isotherm. So that's, as I keep saying, isothermal process. Okay, so by definition, it's the same temperature, so our internal energy change is going to be U. We see that our volume is going up. We're going from a low volume to a higher volume. So the work done on the gas is going to be negative. Okay, and therefore, if there is no internal energy change and we have negative work done on the gas, then we're going to have a positive Q. Okay, so heat's going to flow in, and therefore we're going to basically do work on the gas. All right, and that can be seen here as our temperature. I'm sorry, they have a 300 coming in there. Alrighty, now let's look at 2 to 3. So in 2 to 3, we're jumping from the isotherm here to another isotherm here. And we can see we're going up in temperature. Our volume is going up as well, and the pressure is going down. Now, normally this would sound like an isothermal process because pressure going down, volume going up. But we can see clearly that the temperature is changing. In fact, it is a positive. Make sure I got that right. No, I'm sorry, it's a negative change in internal energy. So when this process, where we have a jump from one isotherm to another, that it has a change in pressure and volume. And if you look at the process 2 to 3 here, there is no heat being added in. Okay, so by definition, what's going on here is there's no heat flow, and this is called adiabatic. Okay, so that's an important process. It's kind of unusual, where we can have no heat flowing in, but because of negative work done on the gas, right, we're compressing the gas. I'm sorry, we'll have a negative internal energy. So, sorry, we're expanding the gas there, and when you have an expansion of the gas, then you're going to have a lowering temperature. And we'll talk about how you can use adiabatic expansion as a very powerful cooling effect. You can see this with gas grills or CO2 cylinders. Again, adiabatic, no heat flow. That's the key thing about an adiabat. All right. Now, from 3 to 4, we're staying along the 200 isotherm. So I'm not going to name that again, but again, there is zero internal energy change, but we are compressing the gas. Okay, so if we're compressing a gas, we have a negative change in volume. Negative times a negative means a positive work done on, and so we have to have heat flowing out in this case. And then lastly, from 4 back to 1, we see we're jumping from the cold isotherm to the high isotherm. We see that curve, so that tells us that's an adiabatic compression. All right, so by definition, it is zero heat flow. We've gone from low temperature to high temperature, so there's a positive change here, and therefore there's going to be a positive work done on the gas. So when you compress a gas very quickly, as I showed you with the fire syringe back a few weeks, that's a very quick warming process because of that work being done on that without any heat flow. All right, so the key thing about this, we're not putting in the numbers like we did in the previous one, is that what Carnot realized, this is the best efficiency, the ideal efficiency you can get when you go through these 4 particular steps. And so he derived an equation, which I'm not going to derive because it requires calculus, that gives us something called the Carnot efficiency. So when you hear Carnot efficiency, it's the optimal efficiency, and it's not 100%, never will be. So it turns out that the Carnot efficiency is based on temperature. It's 1 minus the cold temperature divided by the warm temperature that you're working with here. So in this particular example, we are working with a cold temperature of 200, and we started at 300, so it's going to be 1 minus that, which is 1 minus 2/3, or 0.33. So in this case, it's not very efficient. And we can see that if we want to increase our efficiency, we want a bigger temperature difference, as big as temperature difference as possible. All right, so new things on this before we move on. We have a Carnot efficiency, which is different than the actual efficiency. Actual efficiency will always be less than that. So if we were to work out the numbers here, we would find that in reality we might get less than 0.33. Secondly, we see a new process, adiabatic, which by definition gives us 0 heat flow, but we certainly can get temperature change. Students often think that 0 heat flow means no temperature change. That's not true. All right, so let's sum these processes all up because you want to recognize them. So I'm going to draw an isobaric on a PV diagram for all these, and I'm going to go in one particular direction, and then you just reverse it for the other direction. So let's do an isobaric. So what does that mean? Constant pressure. So I'm going to do this. It's going to be a horizontal line, and let's say I go to the left here. Okay, so what stays constant? Well, by its name, it's pressure. Okay, and what that implies then that volume and temperature stay the same. I'm sorry, temperature stays the same there. I'm sorry. Goof that up. Here we see volume is changing and temperature is changing. Pressure is staying the same. In fact, if we move to the right, and this is something to recognize, that's a positive delta T. Therefore, it's a positive delta U. Again, if we reverse this, go to the left, and then these would become negatives. We can see that the volume is expanding. So if we're expanding the volume, then we have negative work on there. And if we have negative work on there with a positive delta U, okay, the only way we can get that is if we have a positive Q, right? We have to have a greater positive Q than a negative work on to get a positive change in internal energy. All right, isovolumetric would be vertical, so I'll just go up in this particular case. What stays constant? Volume, so that implies a pressure and temperature change. What's the temperature doing here? Well, if we go back to previous ones, we can basically what we're doing is we are changing the volume while changing the volume, pressure, while we're keeping the volume constant. And so if the pressure is going up, volume's constant, then temperature has to go up. So we have a positive delta U and a positive delta T. There is no change in volume, so the work done is 0. So we have to have a positive Q. And again, if the arrow is down, those will become negatives. Isothermal looks like that, fairly steep. All right, what stays constant there is the temperature, and therefore the internal energy. We have a volume change. It's increasing, so the work done on it, again, is negative. In order to get a 0 change, we have to have a positive Q right there. And lastly, an adiabatic. All right, so I'm going to draw an isothermal just for reference. An adiabat, use a different color, is not quite as steep. It would be something like that. That should be curved. And what stays constant there is not temperature, not pressure, and not volume. Okay, what stays constant is there's no heat flow there. This is an expansion. Okay, once again, we're moving, I guess I should be clear, we're moving to the right. So that's going to be a negative work on there. Therefore, we're going to have a negative change in internal energy. That's really nothing that applies right there. And I think I have an equation that I wanted that goes with this. Yep. So there's an equation that we can look at that says when you have an adiabatic expansion or compression, we see that P times V to the 5/2 power, the 5/3 power, equals a constant. Okay, so it's kind of like a different version of our gas law, which says PV equals nRT. This is saying that even if temperature is changing, when we have an adiabatic compression or expansion, we're going to have a relationship that looks like that. Okay, so let's finish up with an example, or maybe I should have you try this example. I'll do it with you. Okay, so we have, or at least I'll start it. When I don't finish, you can finish. We have a diesel engine, certain initial pressure, initial temperature, so that's 300 Kelvin. We might as well convert that now before we forget to and make a mistake later. And we go through various changings, starting at certain conditions. Okay, so we're going to start with an adiabatic compression, then an isobaric expansion, and so on and so forth. So we're going to start somewhere on the PV diagram, and since I can see that we're going to start with a compression, I'm going to have my volume start somewhere in the middle. I don't know where I'm going from there. Okay, so that's my starting point. I'm going to do an adiabatic compression. So my volume is going to go down, but my pressure is going to go up. And since it's an adiabat, right, we're going to have a curve. So I'm going to think about this, and I'm going to go something like this. Not too steep, fairly shallow, and I'm just going to stop arbitrarily right there. Okay, so I'm going to call that 1. Let's call that 2. And I'm going to put an arrow there to indicate that I've gone to compression. Now I'm going to do an isobaric expansion. Okay, so I want to increase the volume, but I don't want the pressure to change. So that sounds like a horizontal, but I'm going to go to 1/5 the volume, original volume. So I am going to go over double this, right? That sounds like that. That doesn't make sense. All right, let me think about this a little bit more. Do I have those numbers right? Oh, it's an expansion, yeah. So I'm going to go 1/5 the original volume. So I can't go past it. All right, so I'm going to go a little bit right there. Then I'm going to adiabatic expansion back to the original volume. So it's going to look something like this. Right? I'm trying to get back to the same volume. And then I'm going to do a cooling down at constant volume. All right, so the last phase here is going to be straight down like that. We haven't changed the volume, so let me put in numbers 2, 3, 4. So I probably in hindsight could have expanded this a little bit, but I think you get the idea. All right, I'm just going to draw this again just to expand it so it looks prettier even in hindsight. So we have this, 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 and then this. Let me just extend it. So 1, 2, 3, 4. All right. Sketch and label with diagrams, put arrows. Let's make sure we put the arrows in there. I've labeled the numbers, so that should be good enough for right now. What is the pressure after the adiabatic compression? Okay. So we're going to 1/10 the original volume. So that's where we can use that proportion I introduced a few minutes ago. I can say PV to the 5/3, P1 V1 equals P2 V2 to the 5/3. Okay, so I want to know pressure afterwards. In other words, I want to know P2. So P2 is going to equal P1 V1 over V2 to the 5/3 power. Okay, so V1 over V2 is 1/10 divided by 1/5. Right, if I've got that correct, and 1/10 over 1/5 is 1/2, so it's 1/2 to the 5/3, and then you multiply that by the original one. So I'll let you work that out. And then I could ask, what's the temperature of the gas after the compression? Okay, so to get that, I would just do PV equals nRT. Okay, because you're given the something about the temperature, or you're given the initial pressure. Actually, we've got the volume, new pressure, and we're looking for temperature, and we know the number of moles, right? I believe somewhere we're told the number of moles. If not, then we're stuck here. All right, I'll get back to you on that. All right, so upon further review, the way to approach part C is not through the Pivner because we don't have N, but we can say that the new temperature is equal to the old temperature times the ratio in the volume, or V2 over V1, and P2 over P1. We got the ratio of pressures from